Hi friends, so today we start lecture 22 on our helicopter dynamics course, and today I'm going to discuss the natural frequencies of a non-rotating beam, specifically a cantilever beam, and we are going to derive the equation for solving for the natural frequencies of such a beam. I'm Dr. Ranjan Ganguly. Now we start off where we left in the last lecture, and we were at the partial differential equation of the rotating beam. So we had our flexural stiffness term, the inertia term, and the centrifugal stiffening term. Now, as I mentioned before, it's not possible to solve this equation primarily because of the presence of the EI here, which is typically a nonlinear function, and also because of the presence of T here, which is again a nonlinear function in the case of rotating beams. So to get some physical insight into the problem, we are going to make a couple of approximations or simplification. First is we are going to set the tension T equal to 0. And next we are going to consider EI to be constant, and that is a uniform beam. So for a uniform non-rotating beam, I can bring out the EI from the brackets here, and I get a fourth derivative term involving the flexural stiffness, and the term involving the centrifugal stiffening simply vanishes. So this is the much more simple equation for a uniform beam, which you may have seen in your vibration or structural dynamics course. So now once we have this partial differential equation, we have to tell this equation what is the physical system and the boundary conditions. So the boundary conditions are going to be at the root you have W and W dash equal to 0, which means the displacement and the slope is 0, and at the blade tip R is equal to capital R, the moment and shear force are 0, or W double dash and W triple dash are 0. So here I'm using the dash as a shorthand notation for d by dr, derivation or derivative with respect to the spatial coordinate r. Now to get the natural frequencies of this system, we do two things. Firstly, we set the forcing to be equal to 0, because we are dealing with free vibration, and free vibration involves no forcing. The second thing, we presume the solution W can be expressed in terms of simple harmonic motion. So we split this function of R and T into a function involving just R and another function involving just T, and then we substitute this equation into the partial differential equation. So once we do that, we get this equation here. So you can see M gets divided by EI. Because we take the second derivative with respect to time, you get a I squared term which becomes -1 here, and you get the frequency squared term also. So here omega stands for the natural frequency of the system, in this case the beam. So this is our differential equation, and through this approximation we have made, or what we have mandated, we have reduced the partial differential equation into an ordinary differential equation. So the PDE has become an ODE. So now we are going to try to solve this equation, and if you recognize that this is a constant coefficient differential equation because M, EI, and the frequency are all constants, I can assume an exponential solution WR is e to the power PR, where P can be written as the fourth root of M frequency squared by EI. Now if we define lambda as this particular number, then this equation, once I substitute WR is EPR, is going to yield an equation in terms of P, and when I solve that I will get 4 roots. So these are going to be plus minus lambda, 2 real roots, and plus minus I lambda, where I is root of -1. So just to summarize, this was our differential equation for the beam. The roots are lambda and I lambda plus minus, and lambda is expressed in terms of the mass, the flexural stiffness, and frequency square. Now, given these 4 roots, we can write out exponential functions with respect to lambda, minus lambda, I lambda, and minus I lambda. And the result of that would be is the solution would be W of R, and there would be a sine and cosine term which come from I lambda, and there would be a sine h and cos h term which come from lambda. So this is the solution we obtain, and we have 4 boundary conditions for this problem which are going to yield the 4 constants for this problem. So that's the equation in terms of WR, and we already know lambda is in this form. Now if I want to find the natural frequencies of this system, I want to calculate the lambdas, and if I'm able to calculate the lambdas, I can get the natural frequencies because I already know M and EI. So let's put the boundary conditions one by one. We first put the boundary condition that W0 equals 0. So we do that. We get this equation here where I have simply substituted small r equals 0 in all these functions, and therefore this has reduced to the form d plus f equal to 0. So we of course know that sine 0 is 0, cos 0 is 1. We also can show that sine h of 0 is 0 and cos h of 0 is 1. So that's the first equation, d plus f equals 0. Now just to recapitulate, sine hx is ex minus e minus x by 2, and therefore sine h0 can be written as e0 minus e minus 0 by 2, or 1 minus 1 by 0 by 2 equals 0. Similarly, I can write out an expression for cos hx. Now if I put cos h0, I get the fact that cos h0 equals 1. So these are the hyperbolic functions. If I wanted to calculate tan hx, I can simply divide these two equations here. So this is my function for WR, and this is the function for W dash of R. And now I put the second boundary condition, which is that W dash of 0 equals 0, and that gives me the second equation, C plus E equals 0. Now I'm not going to get all the 4 equations. You can get it by differentiating W 2 more times. So you can get W double dash, W triple dash, and put R is equal to capital R and put those to 0. And then we are going to get 4 equations here, and the 4 constants C, D, E, F are shown here. We already got these 2 equations which you can see here. For example, the first equation lets you know that D plus F equals 0, and the next equation lets you know that C plus E equals 0. So again, if you want to differentiate these type of functions, the cos h function, if you differentiate it, you get sine hx. The sine h function, if you differentiate it, you get cos hx. So with this knowledge, you can very easily differentiate those functions as a simple homework problem. Now let's get back to our equation here. Now this is a system of 4 equations, and there is a trivial solution, that is C, D, E, F is 0, but that is not of any interest to us. What is of interest is a non-trivial solution, and we can obtain that by setting this determinant to 0, the determinant of this matrix. And if we do that, we get the equation cos lambda r cos h lambda r equals -1. Now look at this equation carefully. If we realize that lambda r is something like x, it is a variable, we essentially have a nonlinear equation, and we could solve this nonlinear equation using any well-known method such as the Newton-Raphson method. This equation also has many solutions, in fact, infinite number of solutions. To see that, we can rewrite this equation in this form, and what we can do is plot these two functions. So I plot cos lambda r and I plot -1 by cos h lambda r, and you can see that these two plots intersect at all these points, and all these points are going to be the solution of this beam transcendental equation. Also, if you are trying to find the solutions using a numerical method like the Newton-Raphson, you can get the initial guesses from the nearest values of this cosine function. So first guess here, second guess here, third guess here, fourth guess here, and so on. So this way you can obtain the solution to any desired level of decimal points as you want. So there are an infinite number of solutions which are given as follows. So 0.597 pi, 1.49 pi, 5 pi by 2, 7 pi by 2, and so on. So this is a system with an infinite degree of freedom. So that's different from a typical spring mass system we saw before, which all had finite degrees of freedom. So these are continuous systems with an infinite number of degrees of freedom. So now let's return back to our frequency. We had the expression for lambda. From this expression, we can get the following here. If we were to multiply both sides by r square and take lambda square, and from here we can get the closed form equation for the natural frequency of a cantilever beam. So if I plug in the first value here, I will get the first frequency. I plug in the second value of lambda r, I'll get the second frequency, and so on. Now remember that for a beam, I know EI, it's the flexural stiffness, I know M, it's the mass per unit length, and I know R, that's the length or the radius of the blade. And with these I can get the natural frequencies of the cantilever beam. So in the next class we will discuss how to get the mode shapes of the cantilever beam, because that's going to give us beam functions which are widely used in numerical methods for rotating beams. See you then.